Determinants are a scalar value assigned to a square matrix, which means it's a m by m matrix. The rows equal the number of columns. It's mostly useful for two things. One, to see if you can make an inverse matrix, and two, eigenvalues and eigenvectors. It's also used in other applications, like when you take the cross product and you're finding the orthogonal vector. But that's one application of it. So how do you find a determinant? The easiest case is a 2 by 2 matrix. Let's say we have entries A, B, C, D. Actually, let's make that a little bigger. So to define the determinant, we multiply A by D, and then we subtract CB, and that's known as the determinant of this matrix. Crisscross applesauce. If this value is equal to 0, then there is no inverse to the matrix. So the determinant has to be non-zero in order for there to be an inverse matrix. If we do, say, 1, 2, 3, 4, the determinant is just 4 times 1 minus 2 times 3, or 4 minus 6, or negative 2. For larger matrices, the process will be to basically make smaller matrices and repeat the process. A 3 by 3 matrix will involve 3 2 by 2s, and a 4 by 4 will have 4 3 by 3 matrices, and then you break those down into 3 2 by 2s, and then you'll get eventually 12 2 by 2 matrices. Let's first start with a 3 by 3. So a 3 by 3, let's say 1 2 3 4 5 6 7 8 9. What you do first is you're going to go with the first horizontal row. You start here, and then you cross these out, and this 1 is the coefficient of the 2 by 2 matrix. So we have 1 times, and that's 5 6 8 9, and then you have to subtract, and then you go to the next number 2, and then you get, cross this out, 4 6 7 9, and then plus for the 3, and that's 4 5 7 8. This is known as the cover-up method. So if we do the math, it's 1 times 5 times 9 is 45, minus 8 times 6 is 48, Then we have minus 2 times 9 times 4, 36, minus 42, plus 3 times 32, minus 35. So we have negative 3 here, minus 2 times negative 6, plus 3 times negative 3, negative 3, plus 12, minus 9. And this all adds up to 0. The determinants are also really interesting. We can do it another way also, if it's a little more convenient. We could do 1, 2, 3, 4, 5, 6, 7, 8, 9. And then what you do is you do the cover-up method. But you start here, and you cross this out. Oh wait. You start here, and then you cross this out. So that's 4. And then that's 2, 3, 8, 9. And that's going to be a negative right there, because when we take determinants, it's always going to be plus, negative, plus, and it follows that pattern throughout the matrix. Depending on the matrix's bottom right could be positive or negative, but so we have negative 4 times this matrix, and then we have plus 5, and then we do the cover-up method here. 1, 3, 7, 9. And then minus 6, 4, 5, 7, 8. Oops, I did that wrong. One, 2, 7, 8. Now, we could do the math, so minus 4 times 18 minus 24 plus 5 times 9 minus 21 minus 6 times 8 minus 14 negative 4 times negative 6 plus 5 times negative 12 minus 6 times negative 6 minus 65 plus 36, 24. I made a minor mistake here. This is 60. Adding all these up together is 0. So we get the same number as before. We can use any column, basically, or row. For example, if we were to do we could do the bottom row, start here, cross these out. So you get 7 times 2, 3, 5, 6. Remember, so it would go plus, negative, plus. So this would be plus, then negative, negative, plus, negative, plus, negative, plus. One, 3, 4, 6. One, 2, 4, 5. And I'll let the viewer do it, but this will equal 0. So the general pattern with these is you have a top left positive sign and a top bottom right positive sign, and it alternates between positive and negative. Oops. So something like that, just over and over again. I'm not sure exactly why, but this is why. This is what it does. And this isn't a square matrix. Now it's a square matrix, and it has that final entry as a positive. Anyway, thanks for watching.